Hello, my name is Ian Denton, and today we're going to be talking about the effects of trail running on metabolic pathways. This will be using a paper titled Metabolomics revealed that the fittest trail runners show a better adaptation of bioenergetic pathways. So, what is running or what is trail running? Not in the sense of it like it is a physical activity, but what are they in relation to metabolic pathways? Well, running is a highly physical activity, as you all know, that places both aerobic and anaerobic demands on one's body. And your performance is highly influential on how certain metabolites change in your body after a run, whether it be increasing or decreasing. Now, a subset of running, which the paper focuses on, is trail running. This is characterized by running on mountainous terrain, forest trails, or unpaved surfaces. So anything that's not just flat ground. It's also characterized by high intense running or a long duration run, with some trail runs lasting hours on hours of time. Both running and trail running change certain metabolites, like I said, depending on performance, and this is due to how they're partitioned to certain pathways, how they're used up, how they're made, increasing or decreasing. So in this paper, they focus on 35 metabolites and how they change, and what we're focusing on today is how they change in regards to performance of an individual. The definition of performance is basically how long it takes to complete a run, which is seen right here in this graph, and graph C, and right here in graph A. So that's what it is. And so you have, out of the 35 that were analyzed, you had 7 of which that had a significant correlation, both either positive or negative, to performance. Out of the 7, you had 6 that had a positive correlation. Taurine, hypoxanthine, kynureninic acid are some of the most important, which we'll get to taurine and kynureninic acid later in the slideshow. The other 3 not listed were adenosine, serotonin, and tyrosine. Out of the 7, you only had 1 that had a negative correlation. This was glutathione, namely the reduced version. This comes into play later in the PowerPoint. So now we're not going to start with positive correlation, we're going to start with our negative correlation right here. So our negative correlation metabolite being, like I said, glutathione, namely the reduced version. So what do I mean by negative correlation? Well, as I said, performance is basically defined as how long it takes you to complete the trail run. And in this paper, in the study, they found that the longer it took to run the trail, or the higher performance you had, the less post-race glutathione you had in your body. Now this is seen in the graph right down here. You can see that as time increased, or as performance increased, you ended up having lower glutathione levels than compared to right here or up here. So this was your negative correlation. And by analyzing the function of glutathione and how it relates to trail running, we can explain this negative correlation. So first, the function of glutathione. So glutathione is a metabolite that is key to a feeder pathway of glycolysis known as pentose phosphate pathway. Now, pentose phosphate pathway has an oxidative and a non-oxidative phase. And in this oxidative phase, the first step is glucose 6-phosphate, one of the key precursors to glycolysis, being converted to 6-phosphogluconolactone. And this is done through NADP oxidizing glucose 6-phosphate to this. And this is where you have glutathione coming in. Glutathione helps to recycle this NADPH to NADP so you can continue this reaction, then the first reaction of the oxidative phase of the PPP. However, glutathione also has another heavy responsibility as well. Glutathione works to scavenge and reduce reactive oxygen species. It is seen here with the glutathione peroxidase reaction, reducing H2O2, hydrogen peroxide, to water. And as well, like I said, you have the reduced version going to actively hunt a more dangerous hydroxy radical, or reactive oxygen species known as hydroxy radical. But why is this important to how the glutathione decreases as performance increases? Well, the longer you run or the longer you engage in physical strenuous activity, the more generation of reactive oxygen species you have. This is due to the partial reduction of a dioxygen, which is seen right here. You have dioxygen to a dioxygen superoxide radical down to hydrogen, and this can go to hydrogen peroxide or to the hydroxyl radical. Now, glutathione, what it will do is the longer you run, you generate more excess reactive oxygen species. These glutathione reduced molecules, your GSH, will go scavenge and actively reduce these reactive oxygen species to prevent from any muscular oxidative damage to either the leg muscles or muscle tissue in your legs or whatever you're doing when trail running, as well as anything to your lipids, your nucleotides, or DNA. It helps prevent this oxidative damage to these by scavenging and actively reducing these. So with this higher performance rate, the more you run, you have a lower post-race glutathione. And this is seen right here again, as the slower runners have lower concentrations, where you have your faster runners having slightly higher concentrations. This leads us to our first quiz question. So in this quiz question, I want you to explain to me or describe to me the relation that glutathione has with running performance, and why post-race concentration levels of glutathione are different than our pre-race concentrations. And for help, you can reference the previous slides in this lecture, or you can also go to our chapter 14 feeder pathways lecture slides and 14 and 15. Moving on, we get to the positive correlation of metabolites in regards to performance. So what positive correlation means is that as performance increases, or as the time it takes to run increases, you have an increased post-race concentration of these metabolites. And like I said, what we want to focus on is taurine and kynurenic acid, because both of these, as time increases, they obviously increase in concentrations, as you can see right here. And so with taurine, the paper states that it is a novel biomarker in both handling muscular damage and lipid oxidation, as well as osmolar regulation. With kynurenic acid, this is a product of another metabolite known as kynurenine, which is converted from tryptophan. This is important in adipose or fat energy expenditure, as well as mitochondrial respiration. But why is lipid oxidation or lipid metabolism or fat energy expenditure important? Well, even though we haven't really discussed it in class, lipid metabolism is very important when it comes to producing energy. It involves both fatty acid oxidation or triacylglycerol synthesis, but we're namely going to focus on your fatty acid oxidation. So the longer you run, it's going to take these stored fats, which are known as triacylglycerols, in your adipose tissue, and break down these long-chain fatty acids right here. And through the breaking down of long-chain fatty acids, you produce both acetyl-CoA and electron carriers such as NADH or FADH2. These electron carriers can go straight to the electron transport chain, but with acetyl-CoA, this will enter your TCA cycle, go through it and to oxidize pyruvate, and you end up with even more electron transport carriers, such as NADH and FADH2. All these electron transport carriers end up going to the electron transport chain, where you make the bulk of your ATP. Now, this ATP is used to fuel the body in trail running to keep it going. This is an aerobic process, which is key, as, like I said, both trail running and running involve anaerobic and aerobic processes. But what about anaerobic processes such as glycolysis, which we have talked about? Well, glycolysis is not just gone when it comes to trail running. In the beginning of trail running, you heavily depend on glycolysis, either through the intake of glucose beforehand or by glycogenolysis. What happens is your muscle glycogen storages will start to be used to produce glucose 6-phosphate in order to go through glycolysis and produce a final product as pyruvate to either go to lactate or acetyl-CoA. Through this process, you get your net 2 ATP through a very quick process, and you also get 2 NADHs as electron transport carriers. However, as performance increases, the time it takes to run increases, the time it takes to trail run increases, you start depleting your glycogen storage as you start accumulating pyruvate to lactate or pyruvate to acetyl-CoA to the point where glycolysis is no longer viable to reduce the ATP. Now, I'm not saying that there's no glucose in the system. What is happening with glucose, however, is this lactate that is produced from pyruvate is going to your liver through the Cori cycle to produce glucose for the brain and the blood, because with the brain, glucose is the only nutrient that it can use for energy. However, like I said, you end up slowing down glycolysis. It becomes no longer adequate for producing high energy because your glycogen storages are depleted. You have no active input of glucose coming in. So you begin to need to prioritize separate pathways in order to supply your body with the energy needed to continue trail running, which can be seen as acetyl-CoA, where this will enter your aerobic metabolism, like I described before, such as the TCA, go to the ETC and produce these ATP. This leads us to our second quiz question. So in about 2 to 3 sentences, I want you guys to explain the role that glycolysis has in the beginning of trail running and why this performance may change, or why this role may change as performance of trail running increases. And you can use the previous slides to help. You can also use our lecture slides to help. What I recommend is also including what metabolites increase or decrease to show that there has been a change from glycolysis to a separate pathway. So in summary, we first learned that glutathione is significantly negatively correlated to performance, as seen through post-race concentrations being decreasing with performance increasing. Now, this is because the role of glutathione is to scavenge and reduce reactive oxygen species that are building up as running takes place, as longer endurance running takes place. Secondly, we also looked at positive correlation of certain metabolites in response to performance, meaning that they are increasing as performance is increasing, as the time it takes to run is increasing. And through these metabolites, we analyzed that lipid metabolism or fatty acid oxidation is a key energy source to continue our high endurance trail running. Finally, we also included glycolysis because your body is still doing glycolysis in trail running, but really only necessarily in the early stages of trail running. So like I said, in the early stages of trail running, the glycolytic pathway is active and is a forerunner of ATP production. However, as performance increases or as the time of trail running goes on, this pathway becomes limited in its energy supplying ability due to glycogen depletion, and now you must have other pathways performing instead to continue high endurance exercises such as trail running. Well, that was the effects of trail running on metabolic pathways, and I'm Ian Denton. Thank you.